How does the world around us work, and what is real? These questions are not only central to scientific and philosophical discourse, but have been circulating since the dawn of human consciousness. Is there a physical reality that is independent of us? Does objective reality exist at all? Or is the structure of everything, including space and time, created by the perceptions of those observing it? When we think about reality, we often assume that what we see, hear, and experience is an accurate reflection of the world around us. However, two different fields of study, neuroscience and philosophy, offer different perspectives on the nature of reality and how we perceive it. Neuroscience tells us that our brain creates our reality. It takes an input from our senses and creates a model of the world we experience. This model is what we call reality. Our brains use this model to make predictions about what will happen next, based on past experiences and sensory input. But how accurate is this model of reality? Is it possible that our brains are creating a distorted version of the world around us? Research suggests that our perceptions are not always reliable, and that our brains can be easily tricked. Optical illusions, for example, demonstrate how our brains can be deceived by simple visual stimuli. I'll show you later in the video. On the other hand, philosophy tells us that reality is something that exists independent of our minds. It exists outside our brains and can be known through reason and observation. According to this view, reality is objective and exists whether or not we are there to perceive it. However, this raises the question of how we can know anything about reality. If we rely on our senses to perceive the world, and our senses are fallible, how can we be sure that what we perceive is accurate? This is a central problem in philosophy known as the problem of knowledge. One possible resolution to this problem is to rely on reason and logic to understand reality. By using reason and observation, we can arrive at conclusions about the nature of reality that are not dependent on our subjective perceptions. But even this approach is not foolproof. Our reasoning abilities can be flawed, and our observations can be influenced by our preconceptions and biases. So where does this leave us in our understanding of reality? It seems that neither neuroscience nor philosophy offers a complete picture of how we perceive the world around us. The truth may lie somewhere in between a combination of our sensory input, cognitive processes, and reasoning abilities. This business about the distinction between things in themselves and things as they appear has troubled philosophers for years. But what does it have to do with modern physics, specifically the story of quantum theory? In fact, such questions have dogged the theory almost from the moment of its inception in the 1920s. Ever since it was discovered that atomic and subatomic particles exhibit both localized particle-like properties and delocalized wave-like properties, physicists have become raveled in a debate about what we can and can't know about the true nature of physical reality. Parmenides, one of the greatest of the pre-Socratic thinkers, talked about the nature of reality, in which he argues that the world we see is an illusion. The real nature of the world is unavailable to our senses, but accessible to us through reason. Furthermore, this real world is unchanging, unified, and timeless. Parmenides' arguments began with the idea that we cannot have a rational concept of nothingness. Since nothingness can't exist, he held there was no empty space. Without empty space to move into, he maintained motion was impossible. He continued in this way until he refuted the ideas of change, difference, and ending. He then turned to the world we interact with, explaining it as mere appearances. His proposition that our senses are useless when looking for truth has proven enduring. That the physical reality is not real. But what does that mean for us? Reality is a complicated thing, especially when it comes to quantum phenomena. Let's start with the most famous example of quantum indeterminism, the Heisenberg uncertainty principle. In the classical everyday world, there is no issue with measurement. You can take any object you like, whether it's a jet, a car, a tennis ball, a pebble, or even a speck of dust. And not only measure any of its properties as you wish, but based on the known laws of physics, we can predict those properties far into the future. All the equations formulated by Newton, Einstein, and Maxwell are entirely deterministic. If you provide the positions and motions of every particle in your system or the entire universe, scientists can accurately tell you where they will be and how they will move at any future moment. The only uncertainties we encounter are due to the limitations of the measurement tools we employ. However, in the realm of quantum physics, this is no longer the case. There exists an intrinsic uncertainty in how precisely you can simultaneously determine a wide range of properties. If you attempt to measure, for instance, the position and momentum of a particle, the energy and lifetime of a particle, the spin in two perpendicular directions, the angular position and angular momentum of a particle, you will discover that there is a limit to how accurately you can know both of these properties at the same time. The product of these properties cannot be smaller than a fundamental value, which is proportional to Planck's constant. In fact, the instant you measure one such quantity to a very fine precision, the uncertainty in the other, complementary one, will spontaneously increase so that the product is always greater than a specific value. Traditionally, we've viewed the quantum world as inherently uncertain, and this uncertainty can't be entirely eliminated. When you precisely determine a property like the spin of a particle in one dimension, the uncertainty in perpendicular dimensions must increase without limit to comply with Heisenberg's uncertainty principle. In essence, you can't cheat the uncertainty principle. Meaningful knowledge about the actual outcome of a quantum system can only be obtained through measurements. However, there has long been an alternative concept, the idea of hidden variables. In a scenario involving hidden variables, the universe is fundamentally deterministic. Quantum entities have intrinsic properties that could, in theory, allow us to predict precisely where they would end up and the outcome of any quantum experiment in advance. The catch is that some of these governing variables are beyond our ability to measure with our current understanding of reality. If we could access and comprehend these hidden variables, we'd realize that the indeterminate behavior we observe is essentially a product of our lack of knowledge about what's truly happening. With a full understanding of these underlying variables, the quantum universe would appear far less mysterious. One of the greatest physicists of the 20th century was John Wheeler. Wheeler was thinking about this quantum weirdness, about how these quanta sometimes behave as particles and sometimes as waves, when he began to devise experiments that attempted to catch these quanta acting like waves when we expect particle-like behavior, and vice versa. Perhaps the most illustrative of these experiments is shown passing a photon through a beam splitter and into an interferometer, one with two possible configurations, open and closed. Interferometers function by directing light in two different paths and then recombining it at the end, creating an interference pattern based on the difference in the path lengths or the time it takes for light to travel through the two routes. Wheeler's curiosity led him to wonder if these photons somehow knew in advance how they should behave. He would commence the experiment in one configuration, and then, just before the photons reached the end of the experiment, he would either open or close, or not, the apparatus at the end. If the light had pre-knowledge of what it was going to do, you'd be able to catch it in the act of being a wave or a particle, even when you changed the final outcome. In the realm of the physical universe, it's crucial to remember that no matter how confident we are in our logical reasoning and the soundness of our mathematics, experimental results are the ultimate judge of reality. When we conduct experiments and attempt to derive the governing rules from them, we must arrive at a consistent framework. While there are numerous interpretations of quantum mechanics, all equally successful in describing reality, none have contradicted the predictions of the original interpretation. Preferences for one interpretation over another, which many people have for reasons not easily explained, essentially boil down to ideology. No matter how uncomfortable it may be, there's a certain level of weirdness inherent to quantum mechanics that we cannot eliminate. You might not find the idea of a fundamentally uncertain universe appealing, but the alternative interpretations, including those involving hidden variables, are in their own manner equally peculiar. First off, what is consciousness? According to the Oxford Dictionary of Psychology, it's the normal mental condition of the waking state of humans, characterized by the experience of perceptions, thoughts, feelings, awareness of the external world, and often in humans, but not necessarily in other animals. Scientists simply don't have one unified theory of what consciousness is. We also don't know where it comes from or what it's made of exactly. However, there's a gap in our understanding when it comes to consciousness. We can't say for sure whether other living beings or even non-living objects possess consciousness. Humans can relate to animals like dogs and cats, thinking they might have some level of consciousness because we see their facial expressions and behavior. But just because we don't feel a connection to rocks, the ocean, or even the night sky, doesn't mean we can prove that they lack consciousness. This is where a philosophical stance called panpsychism comes into play. This claims consciousness is inherent in even the tiniest pieces of matter, an idea that suggests the fundamental building blocks of reality have conscious experience. Crucially, it implies consciousness could be found throughout the universe. The realm of physics also comes into play when discussing consciousness. Certain scientists propose that consciousness might arise from tiny quantum physics events and other intriguing phenomena that occur at the microscale. These mysterious actions, which can have effects over long distances, somehow occur within our brains and give rise to our conscious thoughts. Renowned physicist Roger Penrose, a distinguished figure in the field and recipient of the 2020 Nobel Prize, has dedicated significant attention to exploring the potential connection between quantum mechanics and consciousness. In his 1989 book, The Emperor's New Mind, Penrose boldly asserted that human consciousness is not governed by algorithms, but rather emerges from the influence of quantum effects. This perspective suggests a fascinating interplay between the mysteries of quantum mechanics and the enigmatic nature of consciousness itself. Let's take a moment to unpack that statement. What does it mean for human consciousness to be described as algorithmic? In essence, an algorithm refers to a set of predictable steps designed to achieve a specific outcome. In the realm of philosophy, the concept of algorithms becomes significant in the context of exploring the interplay between free will and determinism. It raises intriguing questions about whether our actions and choices are predetermined, or if we possess true freedom in decision-making. Are our brains simply cranking out math-like processes that can be telescoped in advance? Or is something wild happening that allows us true free will, meaning the ability to make meaningfully different decisions that affect our lives? Within philosophy itself, the study of free will dates back at least centuries, but the overlap with physics is much newer, and what Penrose claimed in The Emperor's New Mind is that consciousness isn't strictly causal because on the tiniest level, it's a product of unpredictable quantum phenomena that don't conform to classical physics. So after considering all that background information, where does it leave us? If you find yourself scratching your head or feeling a bit uneasy, rest assured that you're not alone. These questions are of utmost importance to those who delve into the realms of philosophy and science, since the answers could potentially revolutionize our understanding of the vast universe surrounding us. The inquiry into whether humans possess free will or not carries immense moral implications. For instance, if we determine that individuals lack free will, how should we approach the issue of holding criminals accountable for their actions? Punishment and moral responsibility would need to be reassessed if we conclude that people could not have chosen differently. These thought-provoking considerations emphasize the profound impact that these philosophical and scientific inquiries can have on our society, ethics, and the very fabric of our understanding of human existence. In physics, scientists could learn key things from a study of consciousness as a quantum effect. This is where we rejoin researchers like Johannes Kleiner, mathematician and theoretical physicist, Sean Tull, a mathematician at the University of Oxford, and Giulio Tononi, a neuroscientist. Kleiner and Tull are following Penrose's example, in both his 1989 book and a 2014 paper where he detailed his belief that our brain's microprocesses can be used to model things about the whole universe. The resulting theory is called integrated information theory, and it's an abstract, highly mathematical form of the philosophy we've been reviewing. In the framework of integrated information theory, consciousness is believed to be present everywhere, but it tends to accumulate in areas where it is crucial for connecting various interrelated systems. Consequently, the human body, being composed of numerous interconnected systems, contains a substantial amount of consciousness, which is referred to as phi in integrated information theory. Phi measures the degree of interconnectedness and integration among the various elements or components of a system. It quantifies the extent to which these elements interact and influence one another, forming a cohesive and unified whole. The concept of phi suggests that consciousness arises from the network of interactions and relationships among the elements of a system. Systems with a higher value of phi are considered to exhibit a greater degree of integrated information and are associated with a stronger presence of consciousness. To calculate phi, researchers analyze the causal relationships between the different components of a system. They explore how the information flows and influences other parts within the system. By quantifying these interactions and assessing their complexity, phi provides a numerical value that represents the level of integrated information within the system. However, it is important to note that phi is not a direct measure of subjective experience or the specific qualities of consciousness. Rather, it serves as a mathematical tool to evaluate the interconnectedness and integration of information within a system, potentially indicating the presence of consciousness. Phi allows researchers to compare different systems and explore their relative levels of consciousness. It provides a framework for understanding the emergence of unified and cohesive experiences within complex systems. The revolutionary thing in integrated information theory isn't related to the human brain. It's that consciousness isn't biological at all, but rather is simply this value, phi, that can be calculated if you know a lot about the complexity of what you're studying. If your brain has almost countless interrelated systems, then the entire universe must have virtually infinite ones. And if that's where consciousness accumulates, then the universe must have a lot of phi. The theory consists of a very complicated algorithm that, when applied to a detailed mathematical description of a physical system, provides information about whether the system is conscious or not and what it is conscious of, meaning that, if there is an isolated pair of particles floating around somewhere in space, they will have some rudimentary form of consciousness if they interact in the correct way. If our consciousness accumulates in areas where interrelated systems exist, then our perception and understanding of reality are shaped by the degree of interconnectedness and integration within our conscious experience. Therefore, when considering the concept of reality not being real, we can explore the possibility that our perception and experience of reality are constructed by our consciousness, influenced by quantum processes and the interconnected nature of our conscious systems. The notion of an illusory reality becomes intertwined with the profound questions surrounding consciousness, challenging us to question the true nature and validity of the reality we perceive. Ask anybody what the physical world is made of, and you are likely to be told matter and energy. Yet if we have learned anything from engineering, biology, and physics, information is just as crucial an ingredient. But how did we come to this mind-blowing conclusion? Well, let's take a peek into the realms of engineering, biology, and physics. These clever folks have shown us time and again that information is just as vital as matter and energy in shaping our reality. It's like a secret ingredient sprinkled throughout the universe, giving it that extra zing of complexity. Think about it. In the realm of engineering, information is the bedrock upon which our marvelous technology stands. Every circuit, every line of code, and every byte of data relies on information to function and bring our digital dreams to life. And let's not forget about biology, the miraculous realm of life itself. Within our very cells, information reigns supreme. The DNA molecules nestled snugly inside our bodies contain a mind-boggling amount of information, like a cosmic library of genetic blueprints. But wait, we're not done yet. Physics, the grand master of the natural world, also has a thing or two to say about information. From the mysterious realms of quantum mechanics to the mind-bending phenomena of black holes, information lurks in the shadows, whispering its secrets to those who dare to listen. By studying the mysterious properties of black holes, physicists have deduced absolute limits on how much information a region of space or a quantity of matter and energy can hold. Related results suggest that our universe, which we perceive to have 3 spatial dimensions, might instead be written on a 2-dimensional surface, like a hologram. Our everyday perceptions of the world as 3-dimensional would then be either a profound illusion or merely one of 2 alternative ways of viewing reality. A grain of sand may not encompass our world, but a flat screen might. Way back in the 1970s, Gerard Hooft started pondering the mysteries of black holes. But instead of simply accepting their gravitational prowess, Hooft had an epiphany. He started to wonder if the information that falls into a black hole is somehow preserved, rather than disappearing into the cosmic void. Talk about thinking outside the event horizon. Enter Leonard Susskind, another heavyweight in the realm of theoretical physics. In the 1990s, Susskind took Hooft's mind-boggling idea and gave it a precise string theory interpretation, and that's how the holographic principle was born. So how does this holographic stuff work? Well, it all stems from the idea that the information that makes up our universe is stored on the surface of its boundaries, like a giant cosmic hard drive. Every tiny bit of information, from the tiniest subatomic particle to the grandest galaxies, is encoded in this ethereal data storage system. It's like a cosmic game of Minecraft, where the universe is built block by block using lines of code. But wait, there's more. Not only does this theory suggest that our reality is a holographic projection, but it also hints at the mind-bending possibility that multiple universes might be floating around in this cosmic data soup. It's like having an infinite number of holographic films playing simultaneously, each with its own set of rules and peculiarities. Reality as we know it becomes just one pixel in a vast cosmic screen, lost among the infinite possibilities. Now, before you start questioning your own existence and wonder if you're just a figment of some cosmic programmer's imagination, let's take a moment to ponder the implications. If our reality is but a projection, what does that say about our perceptions, our experiences, and the very nature of truth itself? It's like realizing that the rug has been pulled out from under your feet, leaving you tumbling through the void of uncertainty. It's going to get weirder now. So imagine this. Your brain, that incredible organ responsible for all your thoughts and memories, isn't just your everyday information storage unit, but instead, it's a hologram. Picture it as a mind-blowing cosmic light show where neurons and synapses dance and flicker like shimmering holographic projections. Here's how the story goes. Carl Pribram, a neuroscientist, looked at the brain and thought, why should memories be confined to just a few measly neurons? Let's scatter it all over the place. So he proposed that memories are encoded in the form of nerve impulses that traverse the entire brain. But wait, it gets even weirder. Pribram drew inspiration from those funky patterns of laser light interference you find in holograms. Well, Pribram thought, why not apply that mind-bending concept to the brain? So he suggested that the brain operates like a giant hologram, encoding and decoding frequencies in a mind-blowing symphony. According to Pribram, this holographic brain of ours is like a translation machine. It takes in all the sensory frequencies bombarding us from the outside world, light frequencies, sound frequencies, electrochemical potentials, and works its magic to transform them into the concrete world we perceive. But here's the real kicker. Pribram argues that it's in the holographic domain of consciousness where all these frequencies get sorted out and transformed into the conventional perceptions we're familiar with. Yeah, that's right. Consciousness gets to play the role of the ultimate illusionist, creating the appearance of our brains, bodies, and everything we consider real. So, what does all this mean for us, mere mortals? Well, it means that the reality we perceive is like a grand illusion, carefully crafted by the mischievous hands of consciousness. Okay, let's say we proved the universe is a hologram. What would that mean for my everyday life? In one strict sense, the revelation that the universe is a hologram would have little direct impact on your everyday life. Your morning routine would remain unchanged, and your dog would continue to wag its tail in all its three-dimensional glory. The laws of physics that govern our existence would still hold true, allowing you to navigate through the world just as you always have. However, on a deeper level, this discovery would have profound implications that shape our understanding of reality. It may not alter the way you brush your teeth or tie your shoelaces, but it would revolutionize our comprehension of the universe and our place within it. Similar to how the knowledge of the Big Bang transformed our understanding of the universe's history, the holographic principle would reveal another fundamental truth about the nature of our reality. It would challenge our conventional notions and shed light on the underlying fabric that governs the cosmos. Similarly, the peculiar principles of quantum mechanics, such as the mind-boggling phenomenon of entanglement, won't exactly rock your daily routine. You can't see atoms and don't notice them doing this at all. But these principles are another basic truth that tells us something utterly unexpected about the fundamental nature of the universe. Proving the holographic principle would be much the same. Living our normal lives, we probably won't think much about the peculiar, counterintuitive fact that we live in a hologram. But the discovery would serve as an important step toward fully understanding the laws of physics, which dictate every action you've ever taken. In this chapter of the video, I'm going to be showing you two different illusions to prove that our brains can be tricked. But first, let me explain something. It is a fact of neuroscience that everything we experience is a figment of our imagination. Although our sensations feel accurate and truthful, they do not necessarily reproduce the physical reality of the outside world. Of course, many experiences in daily life reflect the physical stimuli that send signals to the brain. But the same neural machinery that interprets inputs from our eyes, ears, and other sensory organs is also responsible for our dreams, delusions, and failings of memory. In other words, the real and the imagined share a physical source in the brain. So take a lesson from Socrates. All I know is that I know nothing. One of the most important tools used by neuroscientists to understand how the brain creates its sense of reality is a visual illusion. Historically, artists as well as researchers have used illusions to gain insights into the inner workings of the visual system. Long before scientists were studying the properties of neurons, artists had devised a series of techniques to deceive the brain into thinking that a flat canvas was three-dimensional, or that a series of brushstrokes was indeed a still life. So, visual illusions serve as a bridge between the physical world and our subjective experience, offering a glimpse into the remarkable methods employed by the brain to construct our visual reality. They provide scientists with a captivating avenue to explore the mechanisms responsible for shaping our perception of the world around us. Through the study of these illusions, we uncover the intricate interplay between perception and reality, unraveling the secrets of how our brains make sense of the visual universe. Your pupils may be dilating when you see images like this one as your brain tries to anticipate the near future. Look closely at this hole, and what do you observe? Is the hole moving, growing, or expanding? Actually, it's not doing any of those things. The image is actually static and has much to teach us about how our brains and eyes see the world. Neuroscientists and psychologists tested this illusion on 50 men and women with normal vision and, using an infrared eye tracker, found that the greater a participant's response to the illusion, the stronger the pupil dilation response. They also discovered some people, perhaps even you, can't even see it. Okay, as for the second illusion I promised, fix your eyes on the black dot on the left side of this image. While looking at the black dot, try to monitor the object moving on the right side of the image too. Try to answer this question. In what direction is the object on the right moving? Is it drifting diagonally, or is it moving up and down? Remember, focus on the black dot on the left. It appears as though the object on the right is moving diagonally, up to the right, and then back down to the left. Actually, it's not. It's moving up and down in a straight vertical line. Trace it with your finger to verify. This is a visual illusion that confuses our senses with an alternating black-white patch, suggesting diagonal motion. It teaches us that our perception of reality is imperfect and has recently enhanced scientists' understanding of profound philosophical truths about consciousness. We must recognize that what we perceive is not reality itself, but rather a carefully crafted narrative being presented to us. Our brains work hard to bend reality to meet our prior experiences, our emotions, and our discomfort with uncertainty. They are masters of adaptation, constantly striving to make sense of the world around us in a way that aligns with our existing knowledge and beliefs. Think about how our brains fill in the gaps when we encounter incomplete or ambiguous information. When faced with a blurry image or a fragment of a conversation, our minds effortlessly piece together the missing details, drawing from our past experiences and expectations. We create a coherent narrative, filling in the blanks to make sense of the situation at hand. Emotions also play a significant role in shaping our perception of reality. Our emotional states can color our experiences, influencing what we pay attention to and how we interpret events. A gloomy mood may cast a shadow over even the brightest moments, while a joyful disposition can enhance our appreciation of the world's beauty. And then there's our inherent discomfort with uncertainty. Humans have a deep-seated need for certainty and predictability. We seek patterns, impose order, and create explanations to alleviate the anxiety that arises from the unknown. Our brains strive to reduce ambiguity, often resorting to simplifications and stereotypes to make the world feel more familiar and manageable. But this constant bending of reality comes with its limitations. Our brains can inadvertently lead us astray, creating biases and distortions that skew our perception. We may selectively attend to information that confirms our preconceived notions, ignoring contradictory evidence. We may fall prey to cognitive biases, such as the confirmation bias or the availability heuristic, which can cloud our judgment and lead us to faulty conclusions. Recognizing these tendencies is crucial for navigating the complexities of our everyday lives. It reminds us to approach information with a healthy dose of skepticism, to question our own assumptions and biases, and to seek out diverse perspectives. It encourages us to embrace uncertainty, allowing for growth and open-mindedness. When we look out at the universe today, it simultaneously tells us two stories about itself. One of those stories is written on the face of what the universe looks like today, and includes the stars and galaxies we have, how they're clustered and how they move, and what ingredients they're made of. This story has two parts. The first part is about the universe we see around us, which we understand by just looking at it. The second part is about how the universe became the way it is today. Figuring this out is a bit more complicated. We can study things far away to learn about the distant past, like when the light we see today was first produced. But to truly understand it, we have to use our scientific theories, like the laws of physics and the Big Bang Theory. When we do that, we find strong evidence that before the Big Bang, there was something called cosmic inflation. However, to make our observations match our theories, we have to accept the idea of a multiverse. That's why many physicists believe in the existence of a multiverse. In the 1920s, scientists found strong evidence that the many spirals and elliptical shapes we see in the sky are not just individual stars, but are actually whole galaxies. They also noticed that the farther a galaxy is from us, the more its light gets stretched to longer wavelengths. At first, there were different ideas about what this meant, but as more evidence came in, only one explanation remained. The entire universe was getting bigger, like how dough with raisins in it expands as it bakes. If the universe is getting bigger today, and the radiation in it is shifting to longer wavelengths and lower energy, then in the past, the universe must have been smaller, denser, more even, and hotter. When we consider that matter and radiation are part of this expanding universe, the Big Bang Theory leads to three clear predictions. There should be a vast cosmic network where galaxies grow, change, and group together more as time goes on. We should find a background of low-energy radiation that remains from the early universe when neutral atoms first formed in its hot state. The proportions of the lightest elements, like hydrogen, helium, lithium, and their different forms, should be consistent, even in areas where stars have never formed. All three of these predictions have been confirmed by observations, which is why the Big Bang Theory is the leading scientific explanation for the origin of our universe. It has outperformed all competing theories. However, it's important to note that the Big Bang Theory only describes the very early stages of our universe. It doesn't tell us why the universe had those characteristics. In physics, if you know the starting conditions of a system and the rules it follows, you can make highly accurate predictions about how it will develop far into the future, limited only by your computational abilities and the inherent uncertainties in the system. But what initial conditions did the Big Bang need to have at its beginning to give us the universe we have? It's a bit of a surprise, but what we find is that there had to be a maximum temperature that's significantly, about a factor of 1,000 at least, lower than the Planck scale, which is where the laws of physics break down. The universe had to have been born with density fluctuations of approximately the same magnitude of all scales. The expansion rate and the total matter and energy density must have balanced almost perfectly, to at least 30 significant digits. It must have been born with the same initial conditions, same temperature, density, and spectrum of fluctuations, at all locations, even causally disconnected ones. And its entropy must have been much, much lower than it is today, by a factor of trillions upon trillions. When we encounter questions about the initial conditions, which essentially means why things started the way they did, we have two choices. We can either say that it's that way because it had to be and we can't know more, or we can attempt to find a process that sets up the necessary conditions. The second approach, known as appealing to dynamics in physics, involves trying to create a mechanism that accomplishes three crucial things. It must replicate all the successful outcomes of the existing model it seeks to improve upon, in this case, the hot Big Bang. Any new idea must be consistent with the established principles. It should explain what the Big Bang Theory alone cannot, which includes the initial conditions with which the universe began. Any unresolved issues within the Big Bang must be addressed by the new concept. It must make fresh predictions that differ from those of the original theory, and these predictions should lead to observable, testable, or measurable consequences. So far, the only idea that has met these three criteria is the theory of cosmic inflation, which has achieved remarkable success in all these aspects. In simple terms, inflation theory suggests that before the universe became hot, dense, and filled with matter and radiation everywhere, it was primarily influenced by an immense amount of energy that was a fundamental part of space itself. This energy could be thought of as a field, or vacuum energy. However, unlike today's dark energy, which has a very low energy density, equivalent to about 1 proton per cubic meter of space, the energy density during inflation was enormous, roughly 10 to the power of 25 times, greater than the energy density of dark energy today. The way the universe expands during inflation is quite different from what we're used to. In a typical expanding universe with matter and radiation, as it grows, the number of particles remains the same, causing the density to decrease. This results in a slowing expansion over time because energy density is linked to the rate of expansion. However, in inflation, where the energy is an inherent property of space itself, the energy density remains constant, and so does the expansion rate. This leads to what we call exponential expansion. In this scenario, the universe rapidly doubles in size after a very short time, and then it doubles again, and so on. In a remarkably brief period, a tiny fraction of a second, a region that was initially smaller than the tiniest subatomic particle can expand to become larger than the entire visible universe we see today. During inflation, the universe undergoes significant stretching, and this has several important consequences, including making the observable universe appear flat, regardless of its initial curvature, expanding any initial conditions from the region where inflation began across the entire visible universe, generating tiny quantum fluctuations and spreading them across the universe, making them nearly consistent on all distance scales, but slightly smaller in magnitude on smaller scales as inflation nears its end. Converting the energy of the inflationary field into matter and radiation, but only up to a maximum temperature that's considerably below the Planck scale, yet comparable to the energy scale of inflation. Creating a spectrum of variations in density and temperature that exist on scales larger than the cosmic horizon. These variations are adiabatic, meaning they have a constant entropy, and not isothermal, which means they don't have a constant temperature throughout. These outcomes replicate the achievements of the non-inflationary hot Big Bang theory, provide a mechanism for explaining the initial conditions of the Big Bang, and make numerous new predictions that differ from a non-inflationary beginning. Since the 1990s, and continuing to the present day, scientific observations have validated the predictions of the inflationary scenario, distinguishing it from the non-inflationary hot Big Bang theory. The thing is, there's a minimum amount of inflation that must occur in order to reproduce the universe we see, and that means there are certain conditions that inflation has to satisfy in order to be successful. We can model inflation as a hill, where as long as you stay on top of the hill, you inflate. But as soon as you roll down into the valley below, inflation comes to an end and transfers its energy into matter and radiation. When studying the idea of inflation, physicists have examined various hill shapes, or what they refer to as potentials. Some of these hill shapes work for the concept of inflation, while others do not. The crucial factor for success is that the top of the inflationary hill must have a relatively flat shape. As long as the top of the hill is flat enough, inflation can work as a plausible solution for the initial conditions of our universe. But now, here's where things get interesting. Inflation, like all known fields, is inherently a quantum field. This means that many of its properties aren't precisely determined. Instead, they follow a probability distribution. The more time that passes, the more this distribution spreads out. So rather than picturing the process as rolling a point-like ball down a hill, we can think of it as rolling a quantum probability wave function down that hill. Imagine inflation as a process where you're blowing up a balloon. Initially, you have a small deflated balloon, which represents the size of our universe. As inflation proceeds, it's like continuously inflating the balloon. If it takes a short time for the balloon's size to double, you now have a balloon that's twice as large. Inflate it for the same duration again, and it becomes 4 times larger. Keep going, and it will grow to 8 times its original size. After roughly 100 of these inflations, you'd have a balloon that's expanded to a size much, much larger than when you started. Up to this point, things are a little bit clear. Now let's consider a scenario where the inflationary quantum field rolls down into a valley within a specific region. In that location, inflation comes to an end, and the energy of the field transforms into matter and radiation, and this transition leads to what we recognize as a hot Big Bang. This region might have an irregular shape, but it's crucial that enough inflation occurred within it to account for the observational accomplishments we've observed in our universe. The question that arises is, what occurs beyond the boundaries of this region? Here's the issue. If you insist on having enough inflation to explain the properties we see in our universe, then beyond the region where inflation ends, inflation will persist. When we consider the relative sizes of these regions, we discover that in order to make the regions where inflation ends consistent with our observations, the regions where it doesn't end become exponentially larger. This discrepancy becomes more pronounced as time progresses. Even if there were an infinite number of regions where inflation comes to an end, there would be a larger infinity of regions where it continues. What's more, the various regions where inflation ends, giving rise to hot Big Bangs, will all be causally disconnected from one another, separated by more regions of inflating space. In simpler terms, if we think of each hot Big Bang as occurring in a separate bubble universe, these bubbles don't interact or collide with each other. The result is an ever-increasing number of disconnected bubbles as time goes on, all separated by an eternally inflating space. This is what the multiverse is all about, and why some scientists consider it the default position. We have substantial evidence supporting the hot Big Bang theory, and indicating that the Big Bang started with certain initial conditions for which we lack a clear explanation. When we introduce an explanation for these conditions, like cosmic inflation, it leads to unique predictions. Many of these predictions align with what we observe, while others emerge as consequences of inflation. One such prediction is the existence of countless universes and distinct regions, each having its own hot Big Bang event. When you consider all of these regions together, it forms what we call a multiverse. This doesn't mean that different universes have different physical laws or fundamental constants, or that every imaginable quantum outcome occurs in some other part of the multiverse. It doesn't even confirm the actual existence of the multiverse because this is a prediction we can't confirm, validate, or disprove. However, if the theory of inflation holds and the data strongly supports it, the existence of a multiverse becomes highly likely. You might not like this concept, and you might be unhappy with how some physicists use it, but until a better and viable alternative to inflation emerges, the idea of a multiverse is firmly entrenched. Now at least you understand why it's a prominent and enduring theory. If you have an inflationary universe that's governed by quantum physics, a multiverse is unavoidable. As always, scientists are collecting as much new, compelling evidence as they can on a continuous basis to better understand the entire cosmos. It may turn out that inflation is wrong, that quantum physics is wrong, or that applying these rules the way we do has some fundamental flaw. But so far, everything adds up. Unless they've got something wrong, the multiverse might be inevitable, and the universe we inhabit is just a minuscule part of it. In the world of quantum mechanics, we encounter a certain level of weirdness that's fundamental to the nature of our universe. This weirdness is seen in the behavior of quantum particles, which can exhibit properties that change or become uncertain when measured in different ways. Moreover, when we explore the concept of the multiverse, we find that it is an inevitable consequence of our understanding of inflationary cosmology, which itself is governed by the principles of quantum physics. The idea of a multiverse may seem unconventional and challenging to grasp, but it arises from a consistent framework supported by evidence. Understanding quantum uncertainty and the multiverse can be quite puzzling when compared to our daily experiences, but they offer intriguing insights into the complex and profound nature of the universe. We've come a long way in this video, and I think one of the main points we've proven is that reality is not a fixed, objective entity, but a complex interplay of perception, interpretation, and experience. Throughout our exploration, we've delved into the mysteries of consciousness, pondered the enigmatic nature of the mind, contemplated the possibility of living in a holographic universe, and the possibility of multiple universes. We've seen how our brains construct our sense of reality, shaping and filtering our perceptions to create a coherent narrative. But beyond the fascinating theories and mind-bending concepts, there is a profound message to take away from all of this. It's a reminder that our understanding of reality is ever-evolving, shaped by our individual perspectives, beliefs, and limitations. In a world filled with uncertainties and diverse viewpoints, it becomes imperative to cultivate intellectual humility and open-mindedness. We must approach the quest for knowledge with curiosity, embracing the vastness of possibilities and the richness of differing perspectives. So, as we conclude this exploration, let us carry forward the awareness that our perception of reality is not absolute, but a dynamic and subjective experience. Let us challenge our own biases, question the narratives we encounter, and engage in thoughtful dialogue with others. By doing so, we can transcend the limitations of our individual perspectives and collectively unravel the mysteries of the universe. Together, let's continue to embrace the journey of discovery and uncover the hidden depths of our ever-evolving reality. Thanks for watching and subscribe for more videos.